This the lab deals with chapter 10 material. All right, here's the electron cloud distribution for 1s orbital. Here. When you look at the electron cloud distribution here, you know, the greatest density of dots is right at the nucleus. And so right at the nucleus, we're going to have the peak probability of finding an electron. And so where would the most probable distance for the electron be? Well, you know, if the highest probability is right at the nucleus, then wouldn't that be the most probable distance from the nucleus? You know, right at the nucleus. Not inside the nucleus, but at the nucleus. And so, you know, when you graph this, the graph's going to look like this. Psi squared. Psi squared for 1s orbital is going to max out. Which tells us the highest probability is right here. And so is that where we're going to find the electron most likely? You know, the most likely spot to find the electron is right at the nucleus, you know. It turns out that it isn't. It isn't right at the nucleus. And why is that? You know, because if that's the highest probability, it just makes sense. The reason it isn't is because when we're looking at distance, you know, the distance isn't just a single dimensional. The distance is going to be three-dimensional. There's going to be a spherical area around it. And so if we're looking at right at the nucleus, then, you know, the distance, that spherical area that we're looking at is actually quite small because, you know, it's right at the nucleus. The nucleus is quite small, right? And so one way to visualize this is we divide this into these onion layers, which are these rings here. And these rings are going to have equal thickness. And so when we look at it just as flat in 2 dimensions, you know, when we look at, is the electron going to be within this distance? Well, there's going to be a probability. That probability is going to be given by the number of dots in that ring. And then when we look at this next ring, well, will the electron be in this ring here? You know, and that's going to be given by its probability, that is the number of dots. But take a look at the volume difference. If you look at the volume difference between the first ring and the second ring just has a lot more volume. If the second ring has a lot more volume, it's going to capture a lot more dots. As we go out, the rings get bigger, right? In terms of volume, but the dots become less dense. And so what we're trying to do is we're trying to maximize 2 functions. We try to maximize the probability and the volume of the rings. The volume of the rings are going to increase like this, right? Each of these circles. And the density is going to decrease. And so what we'll try to do is we try to maximize both functions. That is, you know, get the biggest ring possible with the most dots. And so just counting the dots, you know, which of these rings has the most? Well, it's going to be the ring right here where we've maximized the probability and maximized the volume for both. And so we're going to get something like this. This blue line is called a radial distribution function. There are other names for it as well, or RDF. If we look at the radial distribution function, it's going to show us the most probable distance that electron is going to be. And for 1s orbital, the most probable distance here turns out to be 53 picometers, the same as the Bohr orbit. And so this is the effective distance for the 1s orbital here. 1s. So these, the book calls them radial probability distributions, RPDs. The RDFs are very common radial distribution functions in chemistry. So I'll stick with that terminology. Well, here's the radial distribution function for the 1s orbital, and you can see the most probable distance is about 53 picometers. It is 53 picometers. If we look at a 2s orbital here, you know, it's around 6 picometers here. Most probable distance for 2s. If we look at a 2p is much closer, about 4. But didn't I say that both the 2s and the 2p have the same effective distance from the nucleus? Yes, but I said that because you have to normalize it. This is 6 picometers around a spherical three-dimensional volume. When we look at the 2p has one lobe pointing one direction, another lobe pointing another direction. And so even though the electron is closer at 4, you know, the most probable distance for the electron is closer, it peaks at about 4, you aren't normalizing over three-dimensional space. I mean, if you took those two lobes and then just spread it out over a spherical volume, then you would get 6. You know, and so they both have the same effective distance. And the p is going to be closer because it doesn't fill all three-dimensional space. Etc. 3s, 3p, and 3d. Now, this is good at illustrating, you know, these RDFs or RPDs, radial probability distributions, are very good at displaying penetration and shielding. So, you know, if we have a 1s electron here, right? If we got a 1s electron here, what's that going to do to this? Well, it's going to shield the 2s electron, right, from the nuclear charge. And that means the 2s electron is going to see a reduced nuclear charge. A reduced nuclear charge we call Z effective. And then the same thing, that 1s electron will shield a 2p electron from the nuclear charge. But, you know, even though we got shielding here, one of these orbitals, the 2s or the 2p, is more penetrating. That is, you know, there's some probability it could be closer to the nucleus. And so which of these two orbitals is more penetrating? Well, if you look at this, you know, there's very little probability the electron's going to be found close to the nucleus here. You know, probability increases as we go up here. But when we look over here, there's a much higher probability that the electron is going to be found quite a bit closer to the nucleus here. You see this little hump here. We got a node here. And so what we say is that the 2s is more penetrating than the 2p. And therefore, the 2s in a multi-electron atom is going to have lower energy, and 2p slightly higher energy. And the same thing goes here. If we look at it, a 3s is more penetrating than a 3p, which is more penetrating than a 3d. There's pretty much no electron density here in the 3d. And so even though we're going to have shielding, you know, the 3s are going to be lower in energy, 3p slightly higher, and 3d quite a bit higher in energy. This makes things a little bit complicated because you know, when we talk about sublevels and subshells and that kind of stuff, so let's go through some terminology just to make sure that we're okay with this. And so when we're thinking about it, for one electron species, we have one s, and then we got the 2s, and then the 2p's. 1, 2, 3 of those. And 3s, 3p, and then the 3d, 2, 3, 4, 5. So we got these orbitals like this. And then what we say is that these are energy levels. And how many orbitals are in each energy level? There are n squared orbitals in each energy level. Okay. Then we have sublevels, although, you know, or sometimes we call these shells here for one electron. You know, this would be the first shell, this would be the second shell. We don't necessarily do it. I mean, it's just one electron, so we usually say just energy level, because there aren't shells of electrons here, like core electrons, and valence electrons. But we also have sublevels. How many sublevels are there in each level? A sublevel would be, well, we have the 1s sublevel. Here we have the 2s sublevel, or the 2p sublevel. And so the sublevel is the L's, you know, and how many L's are there for each energy level? Do you see a pattern? Yeah, we say there are 2, or n, in n equals 2, 3, when n equals 3, so there are n sublevels. Here. Okay, we don't have things like valence and core electrons in a one electron species. There's only one electron. And so the electron's either going to be in the ground state, which is the lowest energy state possible. In this case, it's 1s. Or in an excited state, which is a higher energy state. Yeah. Now, when we deal with multi-electron species, it gets mixed up a little bit. Because here, we got the 1s here. I'll just write it a little differently. 2s here, 2p. The 2p are going to be higher in energy. But still, these are close enough to the same energy. And then we have the 3s, and then the 3p. But the 3d are quite a bit higher in energy. And actually are with the 4. And so it goes 4s, and then a little higher in energy is a 3d, and then a little higher in energy are your 3p's. And so the 4s. Now, where the 4, not 3p's, 4p's. Where's the 4d though? The 4d is actually up here, quite a bit higher in energy. And so what we have here are shells. And so we have the first shell here of orbitals. And then we have the second shell here. Then we have the third shell. Now the third shell is missing a sub-level. Which sub-level is it missing? It's missing the 3D, or the L equals 2 sub-level. And so when we're thinking about energy levels, you know, the energy level is N. And so if we look at the energy level is like this, the 3s, the 3p, and then the 3d, but those aren't really closely spaced in energy. They just have the same N value. Whereas the shells here, well, how many shells are there in the third subshells? How many subshells are there in the third shell? Two subshells in the third shell. Well, how many sub-levels or subshells are there in the third energy level? In the third energy level, there are 3. Right? And so when we're dealing with multi-electron, when we're talking about the third shell, we're just talking about the 3s and 3p, the other subshells up here. And so when we're thinking about it, this is, yeah, there are N sub-levels or sub-shells. Levels and shells are used oftentimes interchangeably. And so the first level, second level, third energy level. It's a bit different. The other thing that leads to confusion is how we define valence electron, especially with transition metals. And so if we fill up the first shell, that's like helium. If we fill up the first and the second shell, we fill it like this, one at a time, hundredroll. We're like neon. You fill up the third shell, and then we're at argon. And so these are what we call cores: helium core, neon core, argon core. The argon core is all these shells filled. When we have a full shell, that leads to stability, right? To break that shell is going to cost you energy. And so these are the Nobel gas electron configurations. And Nobel gases are quite stable. They're unreactive. They don't want to give up electrons because that would break up the filled shell. And they don't want to gain electrons because we have a partial or incomplete shell. Okay, then we go to 4s. At 4s, we have potassium and then calcium. So potassium has one 4s electron, calcium adds the second there. And then we go to the transition metals. So scandium would be argon. We call it argon, 4s2, 3d. So scandium just has one d electron, so 3d1. We could put it in any of these, spin up or spin down. You know. So for example, what would the quantum numbers for this electron be here? Quantum numbers for that electron would be 3, 2, minus 2, plus 1/2. You should be able to name quantum numbers and also name the orbitals using quantum numbers for all of these. All right, and so we see in the fourth shell, we have how many electrons in the fourth shell? We got 3 electrons in the fourth shell. This is the fourth shell. Right. So we got 3 electrons in the fourth shell. And so you think there are 3 valence electrons because valence electrons are the number of electrons in the outermost shell, correct? This is the definition most people learn in Chem 4. You know, the outermost or shell are the valence electrons. Is that what you guys learned? Or what did you learn? Tell me. What did you learn? Well, what I'll tell you, in Chem 1A, we aren't going to use that definition. In Chem 1A, we use the definition I gave you yesterday, which is what? Valence electrons are the highest N level. And so this is very weird because you'd think the 3D would be the valence electron, right? come pluck that up, but it's not. And so sometimes we rewrite this electron configuration. This is the filling order. The 4s2 fills before the 3d1. But we write it in numerical order to show the valence. And so up to here, we call these core electrons, and then past here, we call these valence. Or these core electrons, they're not really core perfectly because, you know, core, we usually have filled shells. And so maybe I'll call these inner shell electrons. Because that 3d1, is that filled? No, it's not filled. But it is an inner shell. Even though, you know, core is probably not the right word, inner shell might be better here. The 3d1 electron is considered inner shell. Why? Because in a 3D orbital, the most probable distance is around here, around 8, 9 picometers, right? But in a 4s, where do you think the most probable distance is? If we take the hydrogen atom as an example, then, you know, the 3, n equals 3, are 9 times a naught, or 53 picometers, 9 times a naught. An n equals 4 orbital would be 16. And so if this is about 9, then the 4 would be around 16. So when we're thinking about it, the valence electrons are more probably defined as the outermost electrons, right? And so which one are the outermost electrons? The 4s or the 3d? The 4s are the outermost electrons. And therefore, if an oxidizer comes along, an oxidizer is going to pluck off the outermost electron first, which is the 4s. And so, a lot of transition metals, you know, in fact, all the transition metals have the 4s orbital filled. And so one of the most common charges for transition metals is +2. +2 because an oxidizer comes along and plucks off these electrons. And so oddly enough, the filling order, you know, you'd think you just reverse it, but and then take the D, because the D are the highest energy. Why didn't we take the highest energy? We didn't take the highest energy because those are a lot closer to the nucleus. Well, oxidizer is going to talk the outside, and it's going to pull off a 4s. 4s are more penetrating, so a little bit more stable, but that's the electron that's going to leave first. And so this is one odd thing here, is that this is not the valence shell here. The valence shell is defined as this, you know. This is defined as the valence here in the 4th energy level. And this is actually part of the inner shell, or core. The 4s and the 4p. Well, for scandium, do you know what the most common charge of scandium is? In fact, scandium is a single charge ion, pretty much. Because there's only, all the compounds of scandium show the same charge. Do you know what it is? Is it +2? No, scandium is, in all, pretty much all its compounds, is +3. Which tells me, you know, an oxidizer comes along, it's going to pluck off the 4s electrons first, and then continue the attack to get a 3d electron, if you have a powerful enough oxidizer. And so, when we're looking at this, you know, scandium 2+, we knock off these. Scandium 3+, we knock off the third one, and we're left with argon. Okay, so these electrons get attacked first. Here. Valence electrons are lost first. And so that's something else that's a little bit odd about this. There's a lot of confusion about, you know, energy levels and whatnot, and valence electrons. Okay, now there's another odd thing that happens, and that is filled shells are stable and half-filled shells are stable. Filled shells are most stable. Half-filled shells I should say half-filled subshells. Half-filled subshells also filled shells, subshells. Fix that. Have stability. And this leads to some exceptions in the filling of these. Exception would be with the manganese family and copper family. The manganese is because of the half filled, and the copper is filled. So this is what happens with manganese and other members. With manganese, the electron configuration that we expect is argon, you know, just that whole core up to 4s2, 3d4. Here's 2, 3d4. And so when we look at it, I'm not going to draw the whole energy level diagram. We'll just go argon up to a certain point, and then we'll put the 4s2 electrons here, and then we're going to have the 3d4s here. So this is one electron short from a half-filled subshell. There's the 4s and the 3d, there's not a significant energy difference there. What happens is an electron gets promoted here from the 4s to the 3d. And so what's actually observed for manganese is kind of an odd electron configuration. You wouldn't expect, you would have to memorize it or memorize the half-filled subshells are stable. But for manganese, the observed electron configuration is a 4s1 and a 3d5. 1, 2, 3, 4, 5. You know, when we think about a half-filled subshell, there's symmetry involved here, which stabilizes things. Like if you're going to eat half a cake or half a pie, let's say half a cake, well, you could slice the cake like this and then just remove half of it. Eat that. Right? Well, this shows no additional stability. What you have to do is when you do this, eat the cake, you slice it in half like this to retain the symmetry, and then just take the top half off. You take the top half off, it's still a round cake. Well, when we have this, that is, when we have half-filled and filled, the reason these are is this is what we call spherically symmetric. Filled shells are spherically symmetric. Because when you fill up all those orbitals, you know, in 3 dimensions, you're just going to get a round spherical distribution of electron density, and it's going to be very even. And it helps stabilize things. Half-filled shells are also spherically symmetric. You fill up half the orbitals, you just don't have as many dots, but it's just going to be in all 3 dimensions. Like, for example, the p orbitals. The p orbitals are, you have 3 of them orthogonal to each other. If you fill all 3 of those, it's going to be what we call spherical symmetry. The d orbitals, you got 5 of those. If you fill all those up and add it all together, it just looks like a ball, spherically symmetric cloud of electron density. And so here we get the symmetry. Now that's for manganese. And below manganese is technetium. You would expect technetium to do the same thing, right? Probably rhenium as well. And when we go to copper, we'll take a look at copper. Okay, so promoting an electron is going to cost you energy. But when you get that symmetry, you get that energy in return, and then some. For copper, we have 4s2. We're looking at argon. 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 4s2, 3d9. That's the electron configuration. And so what do you think is going to happen here? Well, there's one electron shy of being a filled subshell. So we're going to promote the electron here. And the observed will be a 4s1, 3d10. And so copper will be argon 4s1, 3d10. So copper can form an unusual charge, you know. What's a charge of copper? Most transition metals are +2, +3, but copper is a +1 and +2. What do you think is more stable, copper +1 or copper +2? You would think copper +1 because if I'm an oxidizer and I'm going to pluck an electron, which of these two electrons will I pluck? The 4s or the 3d? If I'm an oxidizer, I'm going to pluck off one of these 3ds or I'm going to take the 4s. I'm going to take the 4s. Why? Because it's the highest energy electron? No. Yeah, because it's the outermost electron. Good. And so oxidizer comes along, plucks that off, and then copper +1 has an electron configuration, argon 3d10. And you'd expect it to be stable. But an oxidizer can come along and pluck off one of these electrons. And it turns out the D9 configuration is stabilized by other means. But we'll talk about that maybe later. Silver. You know, silver is another example where silver behaves as you'd expect. If we look at silver, silver only has one charge. What is the charge on silver? Silver is only +1, right? Silver is +1, and silver is not argon, but krypton. Krypton, 5s2, 4d9. And so it's 5s2, 4d9. When we look at silver, wow, that's one electron short from a filled subshell. And so what we can do is we can promote one electron there. And so the observed electron configuration for silver is a 5s1, 4d10. And so writing that, it's krypton, 5s1, 4d10. Here, an oxidizer comes along and it's going to pluck off the 5s electron, giving us silver +1. And that's it. And so silver ion has an electron configuration krypton 4d10. Now, is +2 a common charge for silver? No, +2 is not. And so this 4d10 subshell is quite stable. It's not going to react any farther. Whereas copper, it did react a little bit. There are reasons for that. How about nickel? If you look at nickel, nickel is a 4s2, 3d8. And so it's 2 electrons shy. So nickel, does nickel promote the 2 4s electrons into the 3d? And it doesn't. Nickel just stays 4s2 3d8 because it's too much energy to promote 2 electrons, and there's no payoff, not enough payoff for that. And so this type of exception only happens when promoting 1 electron. Oh, okay. And so what we call these, do you know what the copper family is called? Copper, silver, gold? The copper family, those are called pseudo group 1. Pseudo group 1 because they behave like they have 1 valence electron. Well, they do have 1 valence electron, right? And then the 4d10 or the 3d10 or the 5d10 is a stable subshell, unreactive, except for copper. And so gold, a charge on gold, the common charge on gold is +1. Silver +1, copper +1. The most common charge on copper is +2. How do I know that? It's because of the redox table. When copper metal reacts, it forms +2. Now, why does it do that? Why does it upset the 3d10 subshell? Well, you'd have to wait until Chem 1b for that. It has to do with something called crystal field stabilization energy. Zinc, cadmium, mercury, those are called the pseudo group 2 because essentially they have 2 valence electrons. They have 2 valence electrons because what's the electron configuration for zinc? The electron configuration for zinc is 4s2 3d10. So zinc loses those 2 4s electrons and it's not going to want to touch the 3d because it's a filled subshell. And so zinc is always +2. Cadmium is always +2. And so those are the pseudo group 1, pseudo group 2. Now the other transition metals, they'll have variable charge because it depends on how strong the oxidizer is. You know, can the oxidizer pluck off one of the 3Ds? If it can, then you're going to have multiple or variable charge. So for example, iron, the electron configuration of iron is 4s2 3d6. An oxidizer comes along, plucks off 2 electrons, we'll get iron 2, which is 3d6. A stronger oxidizer comes along and plucks off one of the Ds, we'll get 3d5. So iron 3 plus is 3d5, argon 3d5. And that's about it. You'd need an exceptionally powerful oxidizer to get iron +4, right? Which isn't common. But it's possible. And so +2 and +3 are the common charge. Nickel, +2, +3. Titanium, you know, if you look at titanium, you have argon, 4s2, 3d2. And so what are some common charges for titanium? +2 and +4. You lose all those, the D's. Vanadium. Vanadium is interesting. +2, +3, +4, and +5 are the common oxidation states for vanadium. Chromium, +2, +3 are the free ions. And then in compounds, you could have +4, +5, +6, etc. Depending if you apparently lost all those D's. But as a free ion, you know, you can't have those high oxidation states. Cobalt's pretty interesting. Cobalt, you know, cobalt 3 plus is very powerful oxidizer. Cobalt 2 plus is pretty stable. So, all right, so that's the electron configuration, some terminology, and then electron. So let's take a look at the valence electrons. More detail. let's take a look at something like arsenic. How many valence electrons does arsenic have? Well, what is the electron configuration of arsenic? And so, let's look at arsenic. Arsenic is going to be argon, to use the abbreviation here, 1s2, 2s2, 2p6, etc. Argon, 4s2, 3d10, 4p3. 4p3. And so how many valence electrons does arsenic have? 3 valence electrons? Because these no, actually 5 valence electrons. See? 5. This is very confusing to write this way because this is the filling order. Now, okay, the filling order is how it feels, but we need the reactivity order. The reactivity order is the outermost electron is going to be attacked, right? And so this is why oftentimes we'll rewrite this as argon, and then, you know, the distance from the nucleus is going to depend on the n. Right? And so we'll just write it 3d10, 4s2, 4p3. Now we see we have 5 valence electrons. The rest are going to be inner shell or core electrons. Otherwise, everything else looks the same. So oftentimes you're going to see it in this order. This is not the filling order. This is the order in which it's going to react. You know, you're going to pluck off the electrons, essentially. This is the order in which it fills. And there's a difference there. Arsenic. It's not argon. Arsenic. And so, you know, if we have arsenic plus 5, arsenic plus 3 and plus 5 are common for arsenic. If we have arsenic plus 3 oxidation state, that means it's just lost which electrons? The 4p. And if we have arsenic in the plus 5 oxidation states, essentially it's lost all its valence electrons, the 4s and the 4p. Well, arsenic should show similar properties to phosphorus. Phosphorus has how many valence electrons? 5. Nitrogen, 5. Antimony, 5. Bismuth, 5. So all those have 5 valence electrons. So all those form the nitrogen family. Nitrogens, they give names to that family, like pnictogens or something like that. Chalcogens for the oxygen family. Halogens for the fluorine family. Carbon for the carbon family. Boron for the boron family. So no fancy names for those. You don't need to know them. All right, so the quantum mechanics forms the basis of the periodic table, and the periodic table we use to understand chemistry, and therefore quantum mechanics is pretty much the theory underlying chemistry. Quantum mechanics is what we use to understand chemical reactions and everything else dealing with chemistry. Well, let's take a look at some of those things to try to understand. So we're going to apply this in chapter 9. Here. You guys know how the periodic table is defined. What is the definition of a metal? What is the definition of metal? What is the definition of non-metal? What's the definition of a semi-metal? Yeah, metals will have metallic bonding. Yeah. Well, anyway, I gave you some homework problems. The periodic table, they didn't know about quantum mechanics when the periodic table was developed, Mendeleev. And they're just grouping things into similar chemical properties, physical properties. And so metals are defined based on their chemical and physical properties. As far as physical properties go, metals are malleable, they're ductile. You guys know what malleable and ductile are, right? Or not? Yeah, malleable, you can form it into different shapes. Ductile, you can draw it into wire. They display electrical conductivity, good electrical and thermal conductivity. As far as chemical properties go, they tend to lose electrons. They're reducers, right? Fuels. So metals are reducers. And so they were all grouped based on the properties. But it turned out this grouping, when you get into detail and look at the periodic properties, then Mendeleev was able to develop the periodic table and then predict certain unknown elements that were missing, based on periodic trends. And so we should know how the periodic table is broken down. How is the periodic table arranged? Well, it's arranged in terms of shells. Actually, metals are easy to define. Non-metals aren't as easy to define because non-metals, there's a greater variety of non-metals. Some non-metals are totally unreactive, the noble gases. Some are heavily or highly reactive, fluorine. But non-metals tend to gain electrons, etc. And so we already talked about forming ions here. Metals tend to lose electrons. Well, they're going to lose electrons until they get to the nearest noble gas electron configuration. So, for example, potassium has just one valence electron. We lose that, we're at the argon core. Calcium is 2. We lose both of those, we're at the argon core. And so we've already been using this in predicting redox properties. For example, carbon. Carbon has 4 valence electrons, so it could lose all 4, which goes to the helium core, or non-metals. Non-metals tend to gain electrons until they get to the nearest noble gas electron configuration. Here. And so nitrogen's 3 electrons short, oxygen's 2 electrons short, fluorine's 1 electron short, carbon is 4 electrons short. The non-metals will tend to gain, metals will tend to lose. And so these are all easy. These ones here are just nearest noble gas. These ones here are called the pseudo-noble gas electron configurations. The pseudo-noble gas electron configuration is like copper, silver. It's a 4D, 3D subshells filled, And so it's kind of like a noble gas in that we have this filled D subshell, which is stable. And so even though it's not a noble gas, it's krypton and then the 4D10, we call a pseudo-noble gas because of the 4D10 subshell here. And so the common ones would be silver, cadmium, and zinc here. As these are easy to predict. Gallium 3+, well, gallium 3+, take a look at that. Gallium 3+ has 3 valence electrons. You expect to lose those, and you have the D subshell filled. Thallium as well. It's heavy metals. These are dealing with the 18+2. The 18+2 rule is just this. What is the 18+2 rule? In the configuration labeled 18+2, all outer shell electrons except the 2 s electrons are locked, producing an ion with 18 electrons in the next to outermost shell and 2 electrons in the outermost. So, for example, it's tin 2. And so the 18+2 rule is like this. What's a common charge for arsenic? Well, what are the 2 most common charges for arsenic? What were the 2 most common charges for arsenic? +3. Why +3? because we knocked off the p orbital. The p orbital is higher in energy, right, less penetrating than the s. Well, that's the 18 plus 2 rule. The 18 plus 2 rule is we expected a plus 3 charge because that knocks off the p, leaving the s, right? And then we have the 18 electron rule. The 18 electron rule is get rid of the remaining 2, and we have arsenic plus 5. And so it's the same thing. Now take a look at, let's take a look at, for example, what they gave us here, gallium 3 plus. Actually, that's not the one. This is 18. That's 18. Let's look at tin 2. What are the common charges for tin? Plus 2 and plus 4. Why plus 2? It's the p, right? We knock off the p's and leave the s, right? The p's are less penetrating. And so that's the 18 plus 2. 18 because argon is 18 and the s electrons are 2. But we can also lose the 2 and get the 18 electron rule. And so if we knock off the remaining 2, that gives us a plus 4, which is tin 4. Right? And so we can figure out some of these based on the 18 plus 2, like tin 2, arsenic 3, etc. You know, take a look at these. And then others, well, others we don't really know. Iron 2 is easy. Iron 2 because we lost the S and left the D, but iron 3 is a little more tricky. Well, iron 3 you'd expect it because you lose both S's, we have 5 D electrons left. We can lose one, okay, but losing a second one, iron plus 4, is going to cost you a lot of energy because you have to have a powerful oxidizer to generate that high of a charge. In fact, plus 4 ions aren't that common, right? The only time we see plus 4, plus 5, plus 6, plus 7 is when it's stabilized in a polyatomic ion. But as a free monatomic ion, plus 4 just isn't that common because it's going to be quite reactive. Nickel plus 2 is easy, copper plus 2, these are just losing the valence electrons. All these plus 2 charges should be easy. Now the plus 3 makes sense because the plus 3, it should be okay to lose one more electron, but losing more on top of that is going to be difficult. So plus 2, plus 3 is common. There. Okay. These are just observations, but we could use quantum to help us better understand these observations. Do you need to know the 18 plus 2 rule? No. For the test, you don't, because there are 2 ways you can do this. One, just memorize it. Tin, oh, tin is plus 2 and plus 4. Just memorize it. Or 2, don't memorize it and know the 18 plus 2 rule. Because I might ask you something like, what are the common charges of antimony? What would you tell me? Well, I didn't memorize those. Well, what would you think the common charges or oxidation states for antimony are? Or lead, you know? Well, actually, you might just memorize, the families are going to behave the same, right? Lead, what are the common charges for lead? What are the common charges for thallium? Actually, one really common charge for thallium. Thallium, what do you think the common charges for thallium are? Two plus 2? Why plus 2? You guessed or you had it memorized? Well, it's wrong, but if you knew the 18 plus 2 rule, you'd be able to get it. Does anybody know the 18 plus 2 rule now and can tell me what thallium is? I'm going to cover it up here. What is it? What is it? Huh? What's the symbol for thallium? Thallium is super toxic next to lead. You see? TL. Plus 1. Plus 1 is very common charge for thallium. Thallium has been used historically as a poison for murder. unfortunately. Yeah. +1, thallium salts are bad. Which brings me, you know, I think my office mate at UCSB was trying to murder me because she left a tube filled with thallium in my coffee mug. And I asked her, "Why did you leave it?" You know, it was a sealed tube. So she said, "It's sealed. What's the big deal? It's not going to get in your coffee." And then, you know, I was getting very upset because I couldn't. You know, to her it wasn't a big deal. So you got to watch out because some people, they just don't care. You know, you know, a little bit of poison will make you stronger and tougher. You know, build a resistance to it. That's what they think. Anyway, I'm going to stop here. We'll take a break and then continue.